In our digital world, data is constantly flying around. And we hear these words all the time: encoding, encryption, hashing. But what do they actually mean? They sound kind of similar, and people mix them up a lot, but each one is a totally unique guardian of our information. So let's untangle them, shall we?
First things first. Have you ever been searching for something online and you happen to look up at the address bar on your browser and you just see this total mess of letters, numbers, and percent signs? And you think, what on earth is that?
Well, see that little 20% in the middle of your search for Hello World? Believe it or not, that's just a space in disguise. See, browsers can't really handle characters like spaces in a URL, so they have to translate them into a universal format to send them across the web safely. And that simple act of translation, that's our first stop: encoding.
Yeah, the best way to think about encoding is to see it as a translator. Its job isn't to hide information or keep secrets. Nope. It's just there to change the format of data so that different computers and systems can all understand each other. It's just like a human translator helping two people who speak different languages have a conversation.
And this is the most important thing to remember about encoding. It's all about usability, not security. It uses a public, reversible method. It's like a code book that everyone has a copy of. The goal isn't to hide what you're saying, but just to make sure the message arrives correctly, no matter who or what is reading it.
And we see encoding absolutely everywhere. That 20% we just talked about, that's URL encoding. When you attach a picture to an email, your computer often turns it into a super long string of text using something called base64 encoding. Even the QR code you scan at a restaurant to see the menu, that's just encoded information that your phone can quickly translate back. It's all about making data just work.
All right, so encoding is our translator. It makes sure everyone's on the same page. But what if we don't want everyone to be able to read our data? What if we need to send a private message or protect some really sensitive information? Well, that's where our next guardian comes into play.
And this brings us to encryption, the secret keeper. Look, if encoding is like putting a letter in a regular envelope that anyone could potentially open, encryption is like putting that letter inside a locked steel box. The entire goal here is confidentiality.
The magic ingredient for encryption is the key. It takes perfectly readable data, what we call plain text, and scrambles it into an unreadable format called ciphertext. It's basically a super advanced secret code, and the only way to unscramble it and reveal the original message is if you have the correct key. Without that key, it's just total gibberish. Now, encryption comes in two main flavors. First, you've got symmetric encryption. This is where you use one single shared key to both lock and unlock the data. It's really fast, but you have a big challenge. How do you get that secret key to the right person securely? Then you have asymmetric encryption, which is pretty clever. It uses two keys, a public key you can give to anyone and a private key that you guard with your life. Anyone can use your public key to lock a message and send it to you, but only your private key can unlock it. And trust me, you rely on encryption all day, every day. See that little padlock icon next to a website's address? That's HTTPS, and it's encrypting everything between your browser and that website. Those secure messaging apps like WhatsApp or Signal, they use end-to-end encryption to make sure only you and the person you're talking to can read your chats. It is the absolute bedrock of our digital privacy.
Okay, so we can translate data and we can hide it. But what about a completely different kind of problem? What if we need to prove that a file or maybe a password is authentic, that it hasn't been messed with, but we need to do it without ever storing the original? We need something that's a one-way street.
This is where our third and final guardian comes in: hashing. And honestly, the absolute best way to think about hashing is to imagine it as a unique digital fingerprint for data.
So here's what hashing does. It takes any piece of data, could be a single word, could be an entire high-definition movie, and it shoves it through a complex mathematical blender. What comes out the other side is a unique, fixed-length string of characters. We call that the hash. And there are two golden rules here. One, it's a one-way trip. You can never, ever reverse the process to get the original data back. And two, the fingerprint is always the same size, no matter if you started with the word hi or the entire Library of Congress.
And this is why that fingerprint analogy is so perfect. If you change a single letter in a document, or even just one tiny pixel in a photo, the resulting hash becomes completely, wildly, unrecognizably different. It's this extreme sensitivity that makes it so perfect for checking if data is legit.
By far, the most common use for hashing is storing your passwords. When you create an account on a website, they don't store your actual password. No way. They store the hash of your password. Then, when you log in, they hash the password you just typed and see if the two fingerprints match. It's also used to make sure that a big file you downloaded is the real deal and didn't get corrupted or tampered with.
Okay, this sounds perfect, right? Especially for passwords. If a website's database of hashes gets stolen, the attackers can't reverse them to get the actual passwords. So we're totally safe, right?
Well, not so fast. Here's the catch. Hashing is predictable. The same password will always create the exact same hash, and attackers know this. So they pre-calculate the hashes for billions of common passwords. Think password 123 or QWERTY, and store them in these giant lookup files called rainbow tables. If a hacker gets a database of hashes, they don't even try to crack them. They just look them up, and they'll find that common password in a fraction of a second.
So how do we defend against this? How do we break those rainbow tables? We do it with a wonderfully simple but absolutely brilliant technique called salting.
Here's how it works, and it's genius. Before the system hashes your password, it generates a unique, random little piece of data called a salt. It then sticks this salt onto your password, and then it hashes the whole combined string. So now, even if you and I both have the exact same password, like password 123, our unique salts mean our stored hashes will be completely different. And just like that, those rainbow tables become useless.
Okay, wow, we've covered a lot of ground. We've met the translator, the secret keeper, and the digital fingerprint. So for our grand finale, let's put them all side by side and have a final showdown to make the differences totally 100% clear.
Let's break it down one last time. Encoding is for compatibility, making sure data works everywhere. It's easily reversible, and you don't need a key. Encryption is for confidentiality, keeping data secret. It's reversible, but only if you have the secret key. And finally, hashing is for integrity, proving data is authentic. It's a one-way street, it can never be reversed, and there's no key.
So when you're thinking about these three powerful tools, don't get too lost in the weeds with the technical stuff. The single most important thing to remember is the why. What is the job you are trying to do? So just ask yourself, am I trying to translate this data so another system can read it? Then you need encoding. Am I trying to hide this data from prying eyes? That's a job for encryption. Or am I trying to verify that this data is the real deal and hasn't been changed? Then you want hashing. It's all about picking the right guardian for the job. So choose wisely.